It's two of us here, myself, Asim, and my friend Ashwin. We are going to talk about distributed transactions in the context of a database. Uh, Now, this talk we presented at FOSDEM, rather the day before FOSDEM in Brussels, and the audience were mostly Postgres familiar folks. However, all the concepts that we are going to talk about are quite generic and they apply to any database in particular. So uh, we hope that you find our commentary interesting, and if you don't find it interesting, please don't fall asleep. Please ask questions so that we can make it more interesting. I'm going to skip over this one. Okay, so what we see on slides here are the two boxes which represent two independent databases. They exist without knowing about each other. And let's say our friends from labs have written a magical app that is capable of performing updates or inserts across these two databases. And uh, so let's say we have such an app, and that's the bare minimal or the most primitive version of a distributed database that I could imagine. And let's say the app has performed all its updates on both the databases, and it wants to now is the time to commit. So the app simply sends commit messages to both the databases and maybe waits for an ACK. Now this works pretty well if there is no failure, but let's say one of the shards or one of the databases fails after the app has sent commit message. In that case, we have clearly violation of atomicity here, right? Because the effects of this transaction are visible on shard 1, but the transaction is not visible on shard 2. Now, it is kind of intuitive that to address this problem, to guarantee that atomicity all the time, both the shards or both the databases need to somehow collaborate and uh, arrive at an agreement whether to commit the transaction or to abort the transaction at both the databases. So one way to do that is two-phase commit, and to facilitate this agreement, what we need is a third person called DTM, which is Distributed Transaction Manager. Now, the app, instead of directly talking to the databases, the app would ask the DTM to commit a transaction. And once the DTM receives commit message from the app, the DTM is going to perform the commit in 2 steps. In the first step, it is going to broadcast a prepare message to all the databases or the participants. Once the shard receives prepare message from the DTM, it has a choice whether to respond yes or no to that message. And before it responds anything, it logs the response in the persistent store, in its persistent transaction log. So once all the shards or all the participants have responded to the prepare, the DTM logs the fact that it has observed. So the fact could be that either all the shards have responded yes to the prepare message, in which case it will log that all the shards have prepared, or at least one of the shards either fails to respond or responds with a no. In that case, it will log that fact as well. And once the DTM has logged this fact, the phase 1 or the step 1 of the two-phase commit is complete. And in phase 2, something similar happens. If all the shards or all the participants have responded yes, then the DTM sends a commit broadcast, and once a shard receives commit for a transaction, it records the transaction as committed in its local transaction log and responds with an ACK. And when the DTM has received ACK from all the shards for the commit broadcast, it logs this fact and marks the transaction as finished in its transaction log. And at this point, the transaction is completed, or its effects are visible to all other transactions. Now, how does this really enforce atomicity? Uh, to to realize this more clearly, let's look at some failure scenarios. So let's say this is one of the simplest failure scenarios that one can imagine. Let's say in the first phase, shard 2 fails. The DTM has sent prepare broadcast. One of the shards receives the prepare broadcast, responds yes, but the other one fails and does not respond anything. So DTM would be gracious enough to wait for some time for an ACK from this failed shard, and if it does not receive anything, it considers a no as the response, and it marks this transaction as to be rolled back in the subsequent step. And that is what happens. So in the second phase of the DTM is going to broadcast an abort, and the shard that is alive is going to mark the transaction as aborted in its transaction log, but the shard that is dead may or may not do anything. And so in this case, DTM may wait for some time to hope for the shard 2 to come up and respond to the abort message, but it is not obligated to wait forever. So after that interval of time, DTM marks this transaction as aborted, and that is when the transaction has finished. So let's say a shard fails in second phase. So first phase went well. Both the shards have recorded their response in the transaction log as yes to the prepare phase, and then in the second phase, shard 2 failed. But the second phase, once the DTM has decided to commit this transaction, once the DTM has broadcast a commit message, that is when we enter a point of no return, which means the only outcome after DTM has broadcast commit for this particular transaction is to be committed at all the shards. So in this case, DTM has to wait until shard 2 responds with an ACK to its commit. And until then, the transaction remains in progress as far as the DTM is concerned. It may be committed locally as far as the shard 1 is concerned, but the DTM is going to wait forever until it receives an ACK from all the shards for the commit broadcast. So, I'm sorry. Let's hope that shard 2 comes back up, and whenever it comes back up, the first thing it does is looks at its transaction log to see the most recent checkpoint record, and it will start reading all the records, and it will find that it had written prepare record for the transaction, right? Because we saw that in the first phase of two-phase commit is complete. So there has to be a prepare record that shard 2 should find in its transaction log. And the moment it finds the prepare record, it is going to wait for the DTM to for a decision on this transaction. And the DTM, as we saw, is continuously keeping on retrying the commit to commit broadcast to this particular shard. So eventually, when the shard comes back up, it is going to see the commit message for this transaction. It is going to mark the transaction as committed and respond with an ACK to the DTM, and then the transaction would be finally committed. All right, any questions so far? Yes, sir. The transaction will perpetually remain in progress. In Greenplum, we don't let that happen. We do what is called panic, but yeah. yeah, so in such a case, you would typically either fail over to a replica if you have a HA in place, and if that is not the case, then you're it's kind of a failure. You can't proceed. So let's look at a few more failures. Let's say that DTM has crashed, and DTM has crashed after it broadcast prepare message. Now, as you can see, DTM did not receive anything, or before receiving it crashed, so it did not write anything in the in its transaction log. So whenever it comes back up, it finds no evidence of this prepare broadcast in its local transaction log. So the DTM sends another broadcast as part of its recovery procedure, which is called in doubt transaction broadcast. So DTM is asking all the shards for any in doubt transactions. Do they have any prepared transactions that need to be that need a decision from the DTM? And the shards are supposed to respond with all such transactions with a transaction ID and the state in which that transaction ID is, and the response to the prepare message. So let's say both the shards have one such transaction, and both the shards had responded yes to prepare for that transaction, and if that is the response, then DTM would logically send a commit broadcast to commit this transaction. Now let's say DTM crashed in the second phase. DTM after the first phase was complete, DTM crashed, and then the failure scenario is kind of obvious, like it's similar to what we just saw for shards. DTM is going to look at its transaction log and realize that this particular transaction was prepared at all the shards. So the next logical step for this transaction is to commit. So DTM is going to send a commit broadcast and wait for an ACK, and that is how the transaction is going to be committed. All right. So what is the overhead of two-phase commit versus one-phase commit that the first thing we saw, the app sending commit messages? So the overhead clearly is we need a transaction log flush at both the steps of two-phase commit, and every participant has to perform this transaction log flush. And during each phase, there is a network round trip, a prepare message, an ACK, commit message, and an ACK. So clearly this overhead is a lot, but what we gain is we get a guarantee of A and D of the acid properties. So atomicity and durability is what we get with this overhead. So that is a very, very desirable thing. And at this point, I would like to hand over to Ashwin for covering the remaining part of the acid properties, which is even more interesting.
So with two-phase commit, actually we saw that how the acid properties, at least the atomicity and the durability, are maintained, but just that is not enough for a database to work in a consistent fashion. You still need to have isolation, because the queries, if all the queries are running just one at a time, you essentially don't need the isolation aspect, but all the databases essentially support concurrent queries, and there will be a lot of transactions running concurrently. So even if transactions are running concurrently, how do you still guarantee that they get the correct result and consistent results? So isolation is one of the method which is utilized in databases, and the talk is more towards how the problem is solved for distributed database versus not focused on like just one single node database, because single node isolation kind of, I'll just walk through how Postgres does the isolation, but that itself is not enough to solve for the distributed way, and we need something more on top of the single node isolation to make it distributed consistent. So how Postgres essentially solves the isolation problem for just one node and one database is that every tuple has some fields associated in a tuple, which allows it to give information which is used for checking the visibility. If this tuple I should be visible or not. And two major fields which we use are like xmin, which is the transaction ID which is inserting the tuple, and xmax is the transaction ID which replaces or deletes the tuple if anything is updated. So those are the two fields which are utilized for visibility checking, and the basic idea is that the tuple is visible if the xmin is valid. And what does valid essentially means is that if the transaction has been committed or if I am the transaction which inserts it. So those are the two things which define that I can see the tuple or not. And the other aspect is there is a concept of snapshots, which essentially allows you to filter away what are the active transactions in a system right now. And what snapshot allows you to do locally is that whatever are the transactions currently running in a system, those transactions are never considered as valid for the current transaction. So if you start a transaction right now, and when I started this transaction, there are like 3 transactions which are concurrently in progress. Any effect those transactions are making to the database are not visible to me. So that's what it allows, that it keeps track of all the in progress transactions, and effect of those are masked out or filtered out, even if any of those transaction commits when I am actually seeing the results. So that's what one thing it does. And the second thing is any transaction starting after me is considered as a future transaction, and that's the reason even the effects of that are not seen. So with these two rules, essentially it allows you to filter away or provide a complete isolation in just one single node framework. So we are actually going to build on the same notion but for a distributed database. But before we go there, let's see what essentially is a challenge, that even if we have a single node isolation, still how can we get inconsistent results if we are not doing anything on top of it. So the example talks about if you have two transactions, so transaction A and transaction B, which are started together, and then you do an insert from transaction A and transaction B after it, and both of those first go to shard 1 essentially. So on shard 1, transaction A starts first and gets a transaction ID of 10, and then transaction B starts and it gets a transaction ID of 15. And then essentially you do again insert, but the only thing is the order is little flipped, that transaction B does the insert first and then the transaction A does the insert, and these new inserts are going to shard 2. So it's actually going in a different order to shard 2. So shard 2 is receiving the insert for transaction B first, and that's the reason the transaction ID becomes 20 here, and then the transaction ID is 25 for A because it is later. And if transaction B commits, that is where the scenario is where the problem happens, that if you are going to do a select on this accounts table from a distributed query, you're going to get incorrect results, because for shard 1 it works fine, essentially because on shard 1 B was a future transaction to A, so it is only going to give you results of whatever was committed by transaction A, and not going to give any results from B. But on shard 2, the problem essentially happens is B sees the effects of A, because A was started later and B is committed. So from the visibility snapshot isolation, since B was started earlier and is committed, shard 2 results return back results even from B, which is kind of incorrect, that you get 1, 2 and 4. Essentially A should not have seen effects of B at all. Either it should see effect from a full cluster like both the shards, or not all, any of the shard. In this case it sees from one shard and not from another shard, which is kind of a violation to the isolation property in a distributed environment. So how this is essentially solved is we use the concept of global snapshots, And what global snapshots allows you is it allows you a tiered mechanism wherein you will have a global snapshot which will be used for all the global and distributed queries, but we'll still have a local snapshots which will be utilized for only local only queries, or which are not distributed transactions, just local transactions. So it's kind of a tiered model, and this tiered model allows you flexibility where you can have a system which actually supports both global transactions as well as local transactions, and everything will be consistent even if you are using local transactions just on one node. And that's the reason this hierarchical model helps you with. So what it essentially allows you is, anytime you are starting a distributed transaction, it allocates a distributed transaction ID, and it even takes a distributed or global snapshot of the system. So, and for leveraging that, what is done is, since we are anyways going to leverage the two-phase commit, you need a distributed transaction manager. The same job is provided by the distributed transaction manager, that it can allocate a distributed transaction IDs, and it can provide you a global distributed snapshot of what are the transactions right now running in the system. And leveraging the same concept, you actually have global xmin and global xmax and global in progress array, which is utilized when you are checking the visibility of the tuples. So how essentially the logic works is that if a transaction comes to a local shard and reading a tuple, it gets a transaction ID. That transaction ID which we store in the tuples is always local transaction ID of the system. And the first thing the logic does is it actually maps the local transaction IDs to the global transaction ID. And if the mapping is there, means the transaction which inserted was a distributed transaction. So we will be leveraging the global snapshot for figuring out the visibility. But if we try to do the mapping from local transaction ID to global, and we do not find a global transaction ID associated with it, means that transaction which inserted was not a distributed transaction, it was only a local transaction. So that time then we will be leveraging only the local snapshot for figuring out the visibility. So what this allows essentially is, like, it's kind of same what how the functions calls are. It says that it's a tiered model where always the distributed queries will leverage the global snapshot, and all the local queries will only leverage the local snapshot. So in this way you have a hierarchical model where consistency is definitely guaranteed, even if you are locally running a transaction or globally running a transaction in a system. And just to quickly walk through the same example which we had earlier, how global snapshots solve the problem is, when you start the transactions, global snapshot IDs are allocated to it. So when transaction A starts on shard 1, along with the local transaction ID, we do have a global transaction ID associated with it, which is always kept kind of like in memory list. And then on B, we essentially do the same thing. And then even if the transaction goes in a reverse order on different shards, still the first thing which will be looked at is the global snapshot, and based on global snapshot the visibility will be figured out. So in this setting, even if we run a select query, what will happen is this select query being coming from distributed transaction will always leverage the global snapshot, and based on that it can still detect that B is a transaction which is in future for me. Even if it is locally committed, the results are not returned back, because we are not going to leverage the local snapshot, we are only going to leverage the global snapshot for the visibility aspect. So that guarantees that even if it gets committed on a shard, and even if it is started earlier, we don't see the results of it. And similar example is for how even this scheme allows local transactions to provide a complete isolated view and consistent view, is that if you run a select query after you have committed transaction B, just on node 2, it will leverage the local snapshot. It will not have look at the global snapshot, and based on just local snapshot, it knows that transaction B has been committed, but transaction A is still in progress. So it's going to still give you a correct result, which is from this shard's perspective, what is consistent view, and which is essentially returning value as 4. So that essentially explains how the global snapshot scheme allows you to have isolation level. Now, just to talk about different implementation options, you can implement the two-phase commit and the global isolation levels in different way. You can have a pull model which essentially has like distributed transaction manager as a service, and then participants can actually decide in which transactions they want to participate. And it's kind of like pull model where participants go to the DTM and get the global snapshots and get the global transaction IDs, and they are the ones who are initiating the transactions and participating in the transaction. Versus the other is the push model, which is what Greenplum uses and which most of the MPP databases use, is that there is a central coordinator or the master where all the queries or anything starts, and at the start time, that is where we initiate and assign the transaction IDs to it, and even create the snapshots, and that information is kind of pushed to all the participants. So it's like the DTM who decides who should be the participants and pushes the information with that. So there are different implementations. Finally, the concept kind of remains the same. And even for transactions, that's where you can decide on if you want to support global as well as local transactions, or if you want a system which is just global only system, like Postgres XC is just global only system where it doesn't have this hierarchical model. In that, you can implement like just having one transaction ID is what they use throughout the cluster, which doesn't allow you flexibility of having local transactions and global together in one system. So those are choices which you make when you are implementing these things, and that's the way you can decide on what better or provides more flexibility on. So essentially, just to conclude, two-phase commit is what is providing you atomicity and durability, and global snapshot is essentially providing you the isolation level. But still, those are not the only two components which completes a distributed database. There are still problems even despite having these both the systems you may have, and there still needs to be some other component which is required to completely solve the problem. And I think so most of the folks here who are familiar with the GPDB discussion or mailing list have already seen that this problem is kind of what we have, where because of the ordering in which the updates are happening in a distributed system, you can still end up having a global deadlocks, and that's the reason you essentially need some more aspect along with global snapshots and two-phase commit to complete the full distributed system, which provides you full asset capabilities. So kind of like a global lock manager or more centralized component for locking is also required to complete or make it a full generic distributed system. So yeah, that essentially was it. Okay. Are there any questions? Sure. Mm-hmm. It's always for us, we always start from master, and it will be always a distributed transaction even if it is going to a one node. So local transactions, you actually, if you are considering from the domain of Greenplum database, we never use it, but there are some times for support needs and all, we actually go to the segment directly in utility connection, not via master. And that is the time you can actually leverage, because we provide local transaction ID concept. You can fix up the database or do inserts and all, which will become visible from that angle. So if you're directly going to a segment, you're going to leverage the local transaction ID. But if you're always going via master, even if it goes to one node, it always uses distributed transactions. It's always considered distributed transaction. All the transactions which we start on master are distributed transactions, even if it goes and inserts into one node. But we do two-phase commit on all the nodes. So two-phase commit does not do selective commits right now. It's like a broadcast message of prepare and broadcast message of commit. So even if you inserted a tuple in one segment, all the nodes still participate in the commit. Shin. Uh, just master only transactions. There is no concept of master only transactions which we use right now. Yeah, so the scheme allows you to do those kind of things, because that is the reason we have the flexibility, because we support isolation both globally and locally. We would be able to do it, but right now we don't have support for it. And even if in long run, because in long run we definitely want to do that, like for maybe just not for master but for segments, and this is why very far stretched thought, but we want to kind of go there where you can utilize just one of the segments as just maybe single node Postgres node, which is just for that purpose, but it can still do a joins and all with the distributed tables which are there, and you can do that because we have the local and global schemes. If you did not had that, then you are not able to do it. Like Postgres XC would never be able to do just supporting one table in just one segment and still provide you the full view. So it's not there, but it can be done. Yeah. Correct. So for us, we follow the push model where all the transactions start on the master, and that is the reason it seems as like a serial counter which keeps increasing on the master itself. So yeah, it's kind of like serialized at the master and then it's pushed. If you are using the pull model which XC uses, then the DTM is where which acts as a service. That is where the centralization happens, that when query is trying to fetch a global transaction ID, that's where the coordinator assigns it one. So yeah. Okay, go ahead. When we dispatch the query along with the query plan, we actually dispatch the global snapshot to the segments. It won't be kilobytes also, because number of transactions running concurrently is the only thing we need to send. It's like int uh, for one transaction. That's the information we send. So it's not huge. Yeah. Mm-hmm. So it's actually not to do with the DTM. It's more to do with how we treat the segment failures. It's more to do with HA. So what we do is we don't have we always have a pull concept where master always pulls the information from segments. Even if it is a failure scenario, it's like master always keeps polling, and that interval is that segment had any failures or not. If segment fails, it doesn't push any information to master. It sets the state itself that I am failed, and whenever master comes in, it detects it failed and then does. So this delay is kind of coming from there. It's more HA, not transaction related. Yeah. So abort is always triggered by the master. So that in that case the prepare essentially will fail, and if prepare, yeah, so prepare will fail, or it will receive a abort essentially for that case, when because the dispatch thread itself will get killed, and then the gang creation which we have will detect that even master will roll back that transaction, and even before it initiates a prepare, it will initiate the rollback operation for that on all the segments. Okay, good. Okay, thank you.